Bismillahirrahmanirrahim. Let's start our next lecture for heat and mass transfer. In this lecture we would be solving the problems of chapter number 2, the title of which is Introduction to Conduction, and as mentioned before in one of the previous lectures, we are following the 7th edition of heat and mass transfer by Incorpora and Dewitt. Let's start with 2-26. 2-26 says that at a given instant of time, the temperature distribution within an infinite homogeneous body is given as per the following function. So we can see that over here the temperature is a function of x, y and z, so it's not one-dimensional heat transfer case. Assuming constant properties means thermal conductivity would be considered as constant, and no internal heat generation means Q dot would be 0. Determine the regions where the temperature changes with time. We have to determine the regions where the temperature changes with time, means we need to find out the values of x, y and z where the temperature would change with time. So since we are in the business of the time rate of temperature change of temperature with time, and if you recall, till now we have been over 4 equations. Number 1, Fourier's law of heat conduction, minus K delta T over delta X. Newton's law of cooling, Q is HA delta T, and law of radiation means Q is sigma epsilon A T14 minus T surrounding 4. Those were the 3 equations that we had used in chapter number 1, but they can be used anywhere if required. And in the second chapter we have seen the only equation, which was the heat diffusion equation. You may call it one equation or you may call it 3 equations if we are considering the 3 different coordinate systems, but we have dealt with heat diffusion equation in this chapter. Now which equation involves change of temperature with time? In fact, it is the heat diffusion equation. So we would be starting with the heat diffusion equation, and this equation is telling us that the system is Cartesian coordinate system. So therefore we would be starting with the Cartesian coordinate system, heat diffusion equation in Cartesian coordinate system, and it's not difficult to remember it. It's dava by dava x of k dava t by dava x, and then we will write the same terms in y and z, plus q dot is rho c dava t by dava t. So this is the equation, this is the heat diffusion equation. Since k is constant, so we will take k out of the differential sign, so it would be second derivative of t with x, second derivative of t with y, and second derivative of temperature with z. And it says there is no internal heat generation, so therefore this term will not exist anymore. And on the right hand side we would have rho c, and if we divide throughout by k, that has been taken out of the differential sign, so it would then become the right hand side would then become rho c over k, means 1 over alpha times dava t over dava t. So on the other hand side it would remain 1 over alpha times dava t by dava t, whereas on the other side of the equation we have got 3 terms: second derivative of temperature with x, with y and with z. So if we first differentiate temperature with x, so it would be 2x minus 0 plus 0 minus y and plus 0. So this thing has been written over here. For the second term we have to differentiate temperature with respect to y 2 times. So if we differentiate the function with respect to y for the first time, it would be 0 minus 4y plus 0 minus x and then plus 2z, which has been written over here. And then in the last term we have to again differentiate temperature with respect to z twice. So if we differentiate, we will get these quantities. Now upon differentiating for the second time, differential of y with x would be 0, so we will be left with 2 only. Differential of x and z with respect to y would be 0, so we will be left with minus 4 only, minus 4. And differential of y with respect to z will be 0, so therefore we will be left with plus 2 only. It means that dT by dT is 0. So in the end we are getting dT by dT as 0. It means temperature, variation of temperature with time does not exist. So there is no region where the temperature changes with time. That would be our answer, and therefore the system is under steady state conditions. Now let's have the next problem, which is 2-28 of our book. It says uniform internal heat generation at a rate of 5 exponent 7 watts per cubic meter is occurring in a cylindrical nuclear reactor fuel rod. It's not rod, rather it's rod of 50 millimeter diameter. So in a nuclear reactor fuel rod of 50 millimeter diameter, heat is being generated at this rate, and under steady state conditions, as soon as you are told under steady state conditions, so dT by dT would become 0, and under steady state conditions the temperature distribution is of the form TR is A plus BR square. So by looking at this temperature distribution, we can say that it is the case of one-dimensional heat transfer, because temperature is a function of R only. It means that heat would be coming out in radial direction from inner radius to outer radius. Means if we are at different radii, temperature would have different values. And in this equation, T is A plus BR squared, temperature is in degrees Celsius and R is in meters, where A is 800 degrees Celsius and B is minus 4.167 exponent 5 degrees Celsius per square meter. Kindly note that the units of A would be the same as the units of T, whereas the units of B would be degrees Celsius temperature over length square, because the units of A should be the same as the units of temperature, and the units of BR square should be the same as the temperature units. So therefore the units of B would be temperature per square meter, because it is being multiplied with R square. The fuel rod properties are thermal conductivity is 30, density is 1100 and Cp is 800. As soon as you are given Cp, that is an indication that it would be used somewhere, because if you recall, where did Cp exist? Cp was there in the energy storage term. So if you see the value of Cp, probably that would the authors are trying to make you think towards some transient heat transfer states. But right now, for the time being, we are told that under steady state conditions. So right now the system is under steady state condition, unless told otherwise. So in part A, we are being asked to determine the rate of heat transfer per unit length of the rod. So we have to find out Q by L. The rate of heat transfer, Q per unit length of the rod, means Q by L. At R is equal to 0 means the central line, and at R is equal to 25 millimeters the surface. And then in part B, it says that if the reactor power is suddenly increased to a higher value of 10 to the power 8 from 5 exponent 7, what is the initial time rate of temperature change at R is equal to 0 and at R is equal to 25 millimeters. So it is the second part where the value of Cp will be used, where we are being asked to determine the time rate of temperature change, means delta T by delta T, when the reactor power is increased. So of course when the reactor power would be increased, the temperature would start increasing. So we have to find that out, and for that reason we are given the value of Cp in the problem. So as far as part A is concerned, we have to find out Q by L. So we can directly start with minus K dt by dr. There is no need to apply the heat diffusion equation, because we are not asked to find out the heat generated or the time rate of temperature change or things like that. Rather we were simply asked to find out the heat transfer per unit length, and for heat transfer we can start with the Fourier's law of heat conduction. In radial direction it will be minus K dt over dr, and area would be 2 pi RL and not pi r square. Why? Because this is the area 2 pi RL or pi dl, where the heat will come out in radial direction. Suppose that you are at the center of this cylindrical rod, and then you try to reach to the outer surface. So you will move in radially, you will move out in radial direction. So therefore the area that the heat will be incident upon is in fact pi dl, 2 pi RL times dt by dr. So if we now take this length into the denominator of Q, the right hand side would be minus 2 pi kr times dt by dr. And at R is equal to 0, because we have to find out Q by L at two places, at R is equal to 0 and at R is equal to 25 millimeters. So if in this equation we put R as 0, so therefore Q by L would be 0, means there is no heat transfer per unit length at the central line. Now at R is equal to 25 millimeters or 0.025 millimeters, 0.025 meters, we will put those values in here, minus 2 pi k, k of which is 30 and r is 0.025 meters, times dt by dr. So if we differentiate temperature function, which was a plus br square, so differential of a would become 0 and differential of br square would give us 2br. So we will have 2br. So we are given the value of b, and r is 0.025 meters. So we get 98,182 watts per meter as the heat per unit length, as the heat transfer per unit length of the fuel rod. Now in part B, we are asked to find out. So in part B we have to find out the time rate of temperature change if the reactor power is suddenly increased to this new value of 10 to the power 8. So try to understand the question. It says that when the reactor power is increased. So when the reactor power is increased, what will happen is that the temperatures would start going up. The temperatures would start going up, and we have to find out the initial change of temperature with time at these two locations. So since we have to find out the time rate of temperature change, we would be starting with the heat diffusion equation in cylindrical coordinate system. And along with that, since t is a function of r only, since t is a plus br square, so therefore we do not need to write the second and the third terms of the heat diffusion equation. That is why I was emphasizing earlier during the lecture that if you only remember the first term 1 over r dava by dava r of kr dava t by dava r, that would be sufficient in a lot of cases. Plus q dot is rho c dava t by dava t. So starting from the heat diffusion equation in cylindrical coordinate system, the second and the third term will vanish. So we will be left with the first term 1 over r dava by dava r of kr dava t by dava r plus q dot, or q dot nu, the value of which is 10 to the power 8, is rho c dava t by dava t, is rho c dava t by dava t. Now 1 over r dava by dava r of kr dava t by dava r. So dava t by dava r would be 2br, the other things remain unchanged, and this would become 2kbr square, and if we differentiate it with respect to r the second time, so 2kb times 2r would be its differential. So therefore it would become r and r will get cancelled out, and we would have 4kb plus q dot, which is q2 dot, as rho c dava t by dava t. Now if we just put the values, k is given to us as 30 watts per meter Kelvin, b is given to us as minus 4.167 exponent 5, the power level is increased to 10 to the power 8, is equal to density of fuel rod material, which is 1100, times specific heat capacity, which is 800, times dava t by dava t. So dava t by dava t is in fact the time rate of temperature change, the time rate of temperature change in temperature with respect to time. So we get dava t by dava t as 56.8, and the units would be Celsius per second or Kelvin per second, because that is change in temperature. So change in temperature in Celsius is equal to the change in temperature in Kelvin. So therefore what does this mean? That it means that in 1 second the temperature is going up. See, we got a plus 56.8. So in 1 second the temperature is increasing by 56.8 Kelvin or 56.8 degrees Celsius. This is what it means.